Welcome to EPG Pathshala. In the last two modules, we have looked at various aspects of polytomous regression. In this module also, we will look at a recap and a summary of all that we have introduced for polytomous regression models. So to begin with, we will look at the case when we have a nominal outcome. Now you know that when we have a nominal outcome, it means that we have categories which cannot be ordered in any way. So in this case, the appropriate regression model is the baseline logistic model, and we shall first look at this model and its fitting. Next, we shall move on to the case where we have an ordinal outcome. Now, an ordinal outcome means that it is possible to order the categories, and hence it is possible to think of the corresponding cumulative probabilities. That is, if the outcome Y assumes categories 1, 2 to K, which are ordered in some natural way, in the case where we have an ordinal outcome, it makes sense to define cumulative probabilities of Y less than equal to K. Note that these corresponding cumulative probabilities would have had no meaning in the case where Y is a nominal outcome. So in the case where we have ordinal data, we define the polytomous regression models in terms of the cumulative probabilities, probability of Y less than equal to K. However, there are many competing choices, and a very popular choice is the proportional odds regression model. We shall see the justification for the name proportional odds as also the fact that this implies rather strong assumptions about the nature of the association. We shall see that it is possible to motivate the proportional odds model using a latent variable framework, as we have done for binary choice models in the case where we have a binary outcome. Finally, we shall look at some competing models such as the adjacent category or the continuation ratio logistic model. However, all this being said, polytomous regression models are often difficult to interpret, and a simple starting point is often to artificially categorize the outcomes into two categories and to use a logistic regression model as a starting point. Learning objectives for this module. To begin with, we will define the multinomial logit, which is used to model nominal categorical data. Next, we shall focus on models for ordinal logistic regression. We should introduce a latent variable framework which justifies the choice of a very common model, which is the proportional odds logistic regression. And finally, we shall see that there are some alternative and competing models. Polytomous regression, a recap. Polytomous regression is used when we have an outcome whose distribution is specified by the multinomial distribution. So we have a group of, say, m individuals, and for the ith individual, probability of yi1 equal to yi1 to yij equal to yij is ni by yi1 factorial to yij factorial into pi1 to the power yi1 up to pij to the power yij. Of course, the summation of the pij's are equal to 1, and the reason that the p's are dependent on I is that we have a regression setting where the probability of an individual being contained in a particular category depends upon the individual specific covariates. If we have grouped data, then we would have a situation where the ni's could be greater than 1. But typically, we have ungrouped data along with discrete and continuous covariates. In this case, ni is equal to 1, and exactly one of the yij's will be equal to 1, while the rest will be equal to 0. The simplest model which arises in this setting is when we have a nominal response. Y being nominal means that it assumes one of j categories, but these categories do not have any natural ordering. So for example, the outcome could be something like ethnicity. So for example, Caucasian, African and Asian, where there is no natural ordering of these categories. So in this case, we have a nominal outcome, and the common regression model for this is the multinomial logit. As before, we define the linear predictor given by eta ij equal to xi prime beta j, which is equal to log of pij by pi1. Now note that we have defined eta ij for j minus 1 choices, that is j equal to 2 to capital J. Here pi1 is our choice of baseline, that is we are calculating the odds ratio in each case with respect to the first category being used as a baseline. Obviously, we have summation j equal to 1 to capital J, pij equal to 1. The multinomial logit model assumes that pij is equal to e to the power eta ij by 1 plus summation j equal to 2 to capital J e to the power eta ij. Now once we are able to specify the pij's, we know that we have the multinomial likelihood, and we can plug in these expressions and write the likelihood as a function of the beta j's. So note again that we have j minus 1 vectors of beta j with a different vector for each level of j. So once we can write down the likelihood, estimation and inference using maximum likelihood is simple, or at least it is conceptually simple, and in practice maximizing the likelihood would require the use of iterative algorithms. To fit a multinomial logistic regression model in R, we need to call the library nnet. Note that nnet here stands for neural net and the function multinom. So assuming here that we have an outcome variable, which here is denoted by SPID, the multinomial logit regression model is fitted using the command multinom SPID tilde the variables age plus educ plus. The syntax for fitting the multinomial logit model is multinom SPID, assuming that SPID here plays the role of y, tilde the formula for the covariates as in a normal regression model. So here the covariates are age, educ, and income, and we have used the data set NES. We have stored this here in the R object mmod. You can see here that the model has converged, and it has required a rather large 20 iterations as compared to the standard 5 or 6 iterations which are typically used to fit GLN to binary or count data. To see more, so for example, to recover the log odds ratio vectors beta j's, we can run a summary command on mmod, or an easier way to interpret the outcomes could be to try and get the fitted probabilities from the mmod object. In general, the outcome is rather bulky, as it consists of j minus 1 outcome variables, as it consists of j minus 1 vectors of odds ratios, and interpreting the output could be a problem. Thus, even though it is possible to fit logit model with any number of covariates conceptually, in practice, as a starting point, it might make sense to reduce the number of categories, even consider binary categories by clubbing some of the categories and fitting the regression to get an initial sense of the data. Convergence could also be a problem in the case where we have a large number of categories and or a large number of covariates. Let us move on to the case of ordinal multinomial responses. So here again, Pij is used to denote the probability of yi equal to j for j equal to 1 to capital J. The distinction here is that the categories are now ordered. That is, for example, we could be looking at something like preference and categorize the preferences as do not prefer, somewhat prefer, indifferent, strongly prefer, and so on. So here there is a natural ordering. We define the link function g of gamma ij equal to theta j minus xi prime beta. So note that the link function is not applied to the Pij's but rather to gamma ij's. The gamma ij's now represent the cumulative probabilities. So because the categories can be ordered, it is possible to define cumulative probabilities gamma ij, which in this case denotes the probability of yi less than equal to j, and rather than model the Pij's, we shall choose to model the gamma ij's. So g of gamma ij is equal to theta j minus xi prime beta. So here g denotes a link function as in the univariate case. Common choices are the logit, probit, complementary log-log, again as was used in the univariate case. And we shall see on a later slide that there is a generalization of the binary choice argument which provides a latent variable framework for the use of the model given on this slide. So note here that one distinction with the multinomial regression is that we have different intercepts. We have j minus 1 different intercepts theta j, but we have only one vector beta of log odds ratios, that is beta is no longer subscripted by j. The proportional odds model specifies log of gamma j xi by 1 minus gamma j xi equal to theta j minus beta prime xi, j equal to 1 to j minus 1. The justification for the name proportional odds model comes from the fact that if we assume that we have a single covariate, say x, and we compare two values, x equal to x1 and x equal to x2, then it is possible to show that the proportional odds model implies that gamma j x1 over 1 minus gamma j x1, that is, the odds of y being less than equal to j, that is lying in or below the jth category corresponding to a value x1 of x, as compared to the same odds when x takes the value x2, is given by e to the power minus beta prime x1 minus x2. That is, this odds ratio is proportional to the difference in covariates x1 minus x2, and also notice that this does not depend on the category j. Let us move a step back and look at the fitting of the logit models for multinomial responses. So here we are assuming nominal responses. Baseline category logit model, as we have seen before, is given by log of pi jx divided by pi of capital Jx equal to alpha j plus beta j prime x. Here we have decided to use the last category, capital J, as the reference category, and it is possible to obtain the odds comparing any pair of categories using the fact that log of pi ax by pi bx is equal to log of pi ax by pi capital Jx minus log of pi bx by capital Jx, where the relationship alpha j plus beta j prime x would hold for all j equal to 1 to j minus 1. The fitting can be done by noting that the likelihood can be written as log of product j equal to 1 to capital J pi j into xj to the power yij, which simplifies into summation j equal to 1 to j minus 1 yij log of pi j xi plus 1 minus summation j equal to 1 to j minus 1 yij into log of 1 minus summation j equal to 1 to j minus 1 pi j xi, which using the model can be written as summation j equal to 1 to j minus 1 yij into log pi j xi over 1 minus summation j equal to 1 to j minus 1 pi j xi plus log of 1 minus summation j equal to 1 to j minus 1 pi j xi. We can substitute the beta j's in this equation and get the likelihood for the beta j's. Subsequently, we can maximize this function. However, in practice, this is rather complicated because it turns out that when we find the likelihood for the n individuals, log of product I equal to 1 to n, product j equal to 1 to capital J, pi j xi to the power yij, this turns out to be summation j equal to 1 to j minus 1 alpha j into summation 1 to n yij plus summation k equal to 1 to p beta jk into summation I equal to 1 to n xik yij minus summation I equal to 1 to n log of 1 plus summation j equal to 1 to j minus 1 exponential alpha j plus beta j prime xi. Now, there is no easy way to extract the beta j's from this function, and thus any maximization has to be numerical and iterative. It is for this reason that a relatively simpler but somewhat ad hoc fitting approach is used. That is, instead of fitting the joint model, we take pairs of categories. So, we take the jth category versus the appropriate baseline, which we denote by capital J, and fit the logistic model to this truncated sample. This will give us separate j minus 1 models, but of course, the results will always be less efficient than a full-blown maximum likelihood estimation fitted to the joint capital J categories. Moving back to ordinal regression, we have defined the cumulative logit model. The cumulative logit is specified firstly by finding the cumulative probabilities. Probability y less than equal to j given x equal to pi 1x up to pi jx for j equal to 1 to capital J, and then the cumulative logit is given by logit of probability y less than equal to j given x is log of probability y less than equal to j given x by 1 minus probability y less than equal to j given x, which can be written in terms of the pi's as log of pi 1x up to pi jx divided by pi j plus 1x up to pi capital Jx. The proportional odds model will specify logit of probability y less than equal to j given x equal to alpha j plus beta prime x. Now, note that some models often use the specification alpha j minus beta prime x, while some use the specification alpha j plus beta prime x. What this does is to reverse the sign of the log odds ratio, and I would encourage you to work out the relationship between the cases where we use minus and plus as a coefficient for the betas. As I said before, the proportional odds model name comes from the fact that if we take two values of the covariate x1 and x2 and find the corresponding cumulative log odds ratio, this turns out to be proportional to the difference between x1 minus x2, and further this log odds ratio does not depend on the value of j. From the form of the model, if we were to plot the probabilities, note that this is what the curves would look like. So, on the x-axis here we have plotted the covariate x, and on the y-axis we have plotted the cumulative probabilities, probability y less than equal to j. Now, of course, for any fixed value of x, there has to be a monotonic relationship between these probabilities, and each of these has the familiar sigmoid shape of a logistic regression. Further note that each of these has the same slope, and this is due to the fact that we have used the same vector of log odds ratios. A justification for this model comes from a latent variable motivation. So in this case, we assume that there is some underlying variable y star, and if y star lies between alpha j minus 1 to alpha j, we observe the event y equal to j. As before, we can think of y star as some net utility which has an observed part derived from the covariates, which is beta prime x, and an unobserved part epsilon. We can then relate the two as probability y less than equal to j given x is equal to the probability of y star less than equal to alpha j given x is equal to g of alpha j minus beta prime x, where g is now the CDF of epsilon. As before, assuming that epsilon has a logistic distribution will lead to the proportional odds logistic model. There are some alternative cumulative link models. So note that our specification is G inverse of probability y less than equal to j given x is equal to alpha j plus beta prime x, where g can be any monotonic function lying between 0 and 1. So the cumulative log-log link specifies that log of minus log 1 minus probability y less than equal to j given x is equal to alpha j plus beta prime x. There are some competing models, one of which is popularly used is called the adjacent categories model. So here, instead of modeling the event y less than equal to j as opposed to y greater than j, we model the logit of the function. We model the logit of the probability of y lying between category j, given that it lies either within category j or category j plus 1. For further details on the adjacent categories logit and also another rival category model, which is called the logit model applied to the continuation ratio, and to see the situations in which these models could be preferred to the polytomous regression model, you are referred to the book by Agresti. In this model, we have done a recap of all that we learned about polytomous regression. We have first applied this to the case where we have a nominal outcome, that is, we have an outcome which takes one of a fixed number of categories, but there is no natural ordering of these categories. In this situation, we have fitted the baseline logit model. We have seen that while this can conceptually be fitted using maximum likelihood, in practice, there could be problems with convergence. We need to use numerical and iterative methods, and we also need to ensure that we have a relatively parsimonious model formulation. The model can be fitted using the NNet library in R. Next, we have moved on to ordinal logistic regression, and most of our focus has been on the proportional odds model, which is the most common choice. The reason is that it returns a relatively small set of parameters because we assume that the vector of log odds ratios is the same for all categories. Because we assume that the vector of log odds ratios is the same for all categories. This turns out to be a rather strong assumption, but it can be justified using a latent variable framework. Although we have not looked at fitting in this case, fitting of the proportional odds regression model can be used using the Paul R function in R. We have briefly touched upon an alternative, which is the adjacent category logit. There is actually yet another alternative called the continuation ratio logit, and for this and more, I refer you to the book by Agresti.